right, next is surface area of these parametric surfaces. So what we've got then is, let's say our surface is S and it's given by this R of uv, so given by a vector value function, so components x of uv, y of uv, and z of uv, and that's defined over some open region D in the uv plane. So this would be what would give us our bounds on u and v. What we're going to have then is the surface area of this is defined as the integral over s ds. And the way that we're actually going to compute it is we're going to do a double integral over d, so that's going to give us our bounds in terms of u and v. And inside of this integral, what we're going to compute is we're going to do the magnitude or the norm of, we're going to do r sub u of uv crossed with r sub v of uv. And this is going to be a dA integral, so an integral with respect to area, a classic double integral. We have to define what these two are, so they're essentially like partial derivatives, but vector valued partial derivatives. So r sub u is going to be, we're going to take the derivatives component-wise of the vector value function, so it's going to be the partial derivative of x. This one would be with respect to u times I. This would be plus the partial of y with respect to u times j, and then plus the partial of z with respect to u times k. So basically just take all the partials of the components with respect to u, and then r sub v is the same, except the partials are with respect to v. So the partial of x with respect to vi, plus the partial of y with respect to vj, and then plus the partial of z with respect to v times k. And then the inside of here, this is the classic cross product, so you're going to set that up in the determinant, and then we're going to take the magnitude of that. So that will then become no longer a vector valued function, but instead a function of u and v. So by taking that square root of the sum of the squared components. Now I want to take a second and kind of think about, well, we've already looked at surface area, so these should be compatible. So if we think back to when we saw surface area before, we were in section 14.5, and in that case we were looking at surface area of a surface that can be defined as a function. So z is, say, f of xy, and the way that we did surface area was we did the double integral over the region R in the xy plane. Let me add that up here, xy plane. And what we do is the square root of 1 plus f sub x quantity squared plus f sub y quantity squared. And like I said, we're doing a double integral, so with respect to area. So one of the things I want to think about is, are these two definitions compatible with one another? So what I've done then is tried to describe, well, if I have that surface defined as a function, defined as z equals f of xy, we could create a parameterization for it. So the parameterization for it, a simple one would just be to say let x and y be my two parameters, my first two parameters, and then let the z component just be f of xy. So that's kind of like the examples we did earlier. So then we want to try and use this definition to find the surface area and see what we get. So let's find these two vector valued partial derivatives. So r sub, in this case I don't have u's and v's, I have x's and y's, so I'll do r sub x. So r sub x is going to be, we'll have a partial derivative of 1 on I, so we'll have I. Y will just go to 0, so the j component drops out, and then we'll just have the partial derivative of f. So f sub x of xy times k. And then similarly, r sub y. The I component will drop out, we'll just be left with j plus f sub y times xy as our k component. So next what we want to do is cross those, so r sub x crossed with r sub y, which is going to be that determinant form, so we're going to have I, j, k across the top, Then the x derivative, r sub x, is going to be a 1, 0, and then I'll just put an f sub x. I'll leave off the of xy, we can just keep it in our minds. And then r sub y was 0, 1, f sub y. So then when we compute that cross product, we do the I first. So we're going to really end up with I times, we'll have 0 minus f sub x. And then we're going to have minus j times f sub y minus 0. And then we'll have plus k times 1 minus 0. So simplifying that then, this cross product looks like negative f sub x times I, and then minus f sub y times j, and then just plus a k. So this is that cross product that's on the inside here. And then what we need to do is we need to define the magnitude of it. So let me give us a little bit of space here. Try and leave that bottom portion available. So then the magnitude of r sub x crossed with r sub y is going to be the square root. We're going to have negative f sub x quantity squared plus negative f sub y quantity squared, and then plus 1 squared. And we can already kind of see that we're getting what we want here. So this is then going to just rearranging things. We can put the 1 first, and then we would just have these negatives are going to cancel. So we'll just have f sub x squared plus f sub y squared, and this is the square root. So then according to this formula, what we would do is we would have that surface area is going to be equal to the double integral. Notice this one's over D, which is in the UV plane. That's what the x and y would be defined on. But notice we already picked x and y as our parameters, which are the same variables that z was in terms of. Z was of x and y. So the domain R is going to be the same domain as D. They're the same regions, because it's just what are the bounds on x and what are the bounds on y. So both of those are the x, y plane. So this would be over R. And then the inside we would have 1 plus f sub x squared plus f sub y squared. And it would be a dA integral. So we do get the same thing, which is good. So essentially then what this allows us to do is use whichever one is easier in the situation that we're in. So if it's easier to represent our surface with a function, then we can use this definition over here that we had back from chapter 14. But if it's easier to represent our surface with a parametrization or a vector valued function, then we can use this new definition over here. But in the end, they end up giving the same result for the surface area.